Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reid. If you're new here, this channel exists for the quiet hours. Whether you're drifting towards sleep, unwinding after a long day, or simply want something thoughtful in the background while the world outside goes still, these explorations are designed to carry you gently through the deepest corners of the universe. Tonight, we're going somewhere patient, somewhere slow. We're going to follow the stars that have already burned through everything they had and are now doing the only thing left available to them: cooling, fading, waiting out the longest stretch of time the universe has ever asked anything to endure. We're talking about white dwarfs, the quiet remnants of stars like our own sun, small, dense, extraordinarily hot at first, and then, over trillions upon trillions of years, growing dimmer and cooler until they approach something the universe may never yet have produced, something that may not exist anywhere in the cosmos: a black dwarf. A cold, dark sphere of matter sitting silently in the void long after the last star has gone out. Let's dive in. Part 1. What a white dwarf is. To understand what a white dwarf is, it helps to understand what it used to be. Most stars in the universe, including our own sun, are not the massive, short-lived giants that end their lives in spectacular explosions. They are modest, middle-aged stars, burning hydrogen steadily for billions of years. Our sun has been burning for roughly 4.5 billion years and has approximately another 5 billion years remaining before things begin to change. When a star like the sun runs low on hydrogen in its core, the balance it has maintained for billions of years begins to shift. The core starts to shrink under gravity. As the core shrinks, the outer layers of the star respond in the opposite direction. They expand outward, dramatically and slowly, transforming the star into what astronomers call a red giant. The sun, when it reaches this phase, will expand so enormously that it may reach as far as Earth's current orbit. During the red giant phase, the star sheds its outer layers in great, slow pulses. These expelled shells of gas drift outward into surrounding space, forming a glowing cloud called a planetary nebula. The name is a historical accident. Early astronomers thought these glowing rings resembled planets. They have nothing to do with planets at all. What remains at the center of that expanding cloud is the stellar core left behind. It is no longer producing energy through nuclear fusion. It is simply the hot, dense remnant of everything the star used to be, compressed into a sphere roughly the size of Earth, despite containing a mass comparable to the Sun. The density of a white dwarf is almost impossible to fully appreciate. A single teaspoon of white dwarf material, if you could somehow bring it to Earth, would weigh somewhere around 5 tons. The entire object contains the gravitational pull of a star, packed into something Earth-sized. White dwarfs are not rare. Astronomers believe they represent the eventual fate of roughly 97% of all stars in the Milky Way. The massive stars that end in dramatic supernova explosions are the exception. The quiet fade into a white dwarf is the rule. Most stars go this way. The white dwarf generates no energy through fusion. It has no active power source. What makes it glow, at least at first, is the heat accumulated during its entire stellar lifetime, heat that is now slowly radiating away into the surrounding darkness. It is, in the most literal sense, a cooling object. The surface temperature of a newly formed white dwarf can reach 100,000 degrees or more, far hotter than the surface of the Sun, which sits at around 5,500 degrees. Over time, it cools. The glow shifts from ultraviolet to visible white, then yellow, then orange, then red. There is something quietly moving about the white dwarf's situation. It has done everything a star can do. It has burned for billions of years, swelled into a giant, shed its outer layers into space, and left behind this final dense remnant. It is finished with all of that now. What lies ahead is simply time. Part 2. The Physics of the Fade. The reason a white dwarf does not collapse in on itself, despite having no active energy source, is one of the more elegant pieces of physics in all of astronomy. It comes down to a principle in quantum mechanics called electron degeneracy pressure, and understanding it requires a brief look at how electrons behave under extreme conditions. In a normal gas, the pressure keeping it from collapsing is thermal pressure. Heat makes particles move faster, and that motion pushes outward against gravity. Remove the heat, and the pressure drops. In a sufficiently cool and dense gas, gravity would eventually win. This is why cooling things tend to shrink. White dwarfs are different. The electrons packed into a white dwarf's interior are governed not just by temperature, but by a fundamental rule in quantum mechanics, stating that no two electrons can occupy the same quantum state at the same time. This is called the Pauli exclusion principle. When electrons are packed closely enough together, as they are in a white dwarf, this rule becomes physically significant. The electrons resist being compressed further, not because they are hot, but because quantum mechanics simply will not allow them to be squeezed into fewer states than they already occupy. The pressure this resistance creates is called degeneracy pressure, and unlike thermal pressure, it does not depend on temperature. This means that as a white dwarf cools, it does not shrink. The degeneracy pressure holding it up does not weaken as the temperature drops. The white dwarf remains the same size, regardless of how cold it gets. Think of it like a crowded room where every seat is taken. No matter how quiet the people in the room become, you still cannot fit another person in. The room is full, not because of energy or activity, but simply because there is no space remaining. White dwarf electrons are in essentially the same situation. This property was first worked out theoretically in the 1920s and 1930s by a physicist named Subramanian Chandrasekhar, who was working on the problem as a young man travelling by ship from India to England. He calculated that electron degeneracy pressure has a limit, a maximum mass a white dwarf can have and still be supported. That limit, now called the Chandrasekhar limit in his honour, is approximately 1 4/10 times the mass of our Sun. White dwarfs that exceed this mass cannot survive as white dwarfs. They collapse further or trigger a particular type of explosion. But white dwarfs below this limit are stable, essentially indefinitely. Chandrasekhar received the Nobel Prize in Physics in 1983 for this work, more than 50 years after he first did the calculation on that ship voyage. The recognition was long delayed, in part because his results were controversial at the time, publicly dismissed by some of the most respected astronomers of the era. The physics of white dwarf stability is a beautiful example of quantum mechanics operating at astronomical scales. The same rule that governs how electrons arrange themselves in atoms, the rule that determines the structure of the entire periodic table, is also what holds a dead star together across trillions of years of cooling. Part 3. Reading the light they leave. Astronomers learn almost everything they know about white dwarfs from the light those objects emit. The study of that light has revealed a surprisingly rich and varied population of stellar remnants. White dwarfs are not all the same. They vary in temperature, composition, magnetic field strength, and atmospheric chemistry. The spectrum of a white dwarf is produced by analysing its light and separating it by wavelength, the same way a prism separates sunlight into a rainbow. Different elements absorb light at very specific wavelengths, producing patterns of dark lines in the spectrum. By identifying which lines are present, astronomers can determine what elements exist in the white dwarf's atmosphere. Most white dwarfs have atmospheres dominated by hydrogen. These make up roughly 80% of all known white dwarfs. The hydrogen atmosphere is what remains after the outer layers of the original star were shed during the red giant phase, and it floats to the surface because hydrogen is the lightest element, and heavier elements sink rapidly in intense gravity. A smaller fraction of white dwarfs have atmospheres dominated by helium rather than hydrogen. The reason some white dwarfs lose their hydrogen layer entirely is still an area of active research. One possibility is that the hydrogen layer becomes thin enough during cooling that it mixes into the helium below it and effectively disappears from the observable spectrum. Some white dwarfs show traces of heavier elements in their atmospheres, elements like calcium, magnesium, silicon, and iron. This is surprising because the intense gravity of a white dwarf should cause heavy elements to sink below the observable atmosphere within a relatively short time. When they are detected, it means they were delivered to the atmosphere recently. The leading explanation is that these white dwarfs are actively pulling in material from asteroid-like bodies or rocky debris orbiting them at close range. The detection of heavy elements in white dwarf atmospheres has opened up an entirely new field of research into the composition of rocky planetary material from destroyed worlds around other stars. Studies of these polluted white dwarfs have found compositions remarkably similar to the rocky inner planets of our own solar system, suggesting that rocky planet formation is common around stars throughout the galaxy. Astronomers are essentially reading the chemistry of destroyed worlds through the atmosphere of the white dwarf that consumed them. White dwarfs also vary considerably in their magnetic field strengths. Most have relatively modest magnetic fields, but a significant fraction have fields far stronger than the Sun's, strong enough to measurably alter spectral lines of hydrogen, splitting them in ways that would not otherwise occur. These highly magnetized white dwarfs may result from mergers between two white dwarfs. Some white dwarfs undergo periodic pulsations, rhythmic brightness changes driven by pressure waves propagating through their interiors. These pulsating white dwarfs are extraordinarily useful because the frequencies and patterns of their oscillations carry information about the internal structure, the thickness of outer layers, the interior temperature, and even the rotation rate deep inside. The light of a white dwarf, in all its variety and nuance, is a remarkably complete record of what that object has experienced and what it is made of. In a universe where most of what we know about distant objects comes from photons traveling across vast distances, the spectrum of a white dwarf is one of the richer texts available for reading. Part 4. The Exploding Ones. Not all white dwarfs cool quietly. A fraction of them, in the right circumstances, end their existence in one of the most precisely calibrated explosions in the known universe. These are the Type 1a supernovae, and they have played an extraordinary role in our understanding of the cosmos, far beyond what their modest origins might suggest. A Type 1a supernova begins with a white dwarf in a binary system, meaning it orbits another star at relatively close range. The white dwarf accumulates mass from its companion star over a long period of time. Material from the companion falls onto the white dwarf's surface and gradually adds to its total mass. As the white dwarf's mass increases and approaches the Chandrasekhar limit, the conditions in its interior change dramatically. The carbon and oxygen making up most of the white dwarf's interior begin to experience rising temperatures and pressures, At some point, carbon fusion ignites somewhere in the interior, and what follows is a runaway process. In a normal star, if fusion rates increase and the core heats up, thermal pressure increases and the core expands slightly, slowing fusion back down. It is a self-regulating system. In a white dwarf, the pressure is provided by electron degeneracy, which does not respond to temperature. So when fusion ignites, the white dwarf does not expand to compensate. The temperature just keeps climbing. Fusion rates accelerate, and within seconds, the entire white dwarf detonates. The explosion is total. There is no remnant left behind. The entire white dwarf is consumed in a thermonuclear detonation that releases an almost incomprehensible amount of energy in a matter of seconds. The expanding debris cloud can briefly outshine an entire galaxy of hundreds of billions of stars. And then it fades over weeks and months as the radioactive products of the explosion decay. What makes Type 1a supernovae so scientifically valuable is their remarkable consistency. Because the explosion is triggered when the white dwarf reaches approximately the same mass threshold each time, the energy released is roughly the same. Astronomers call objects like this standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. By studying Type 1a supernovae in distant galaxies and measuring their apparent brightness, astronomers can determine distances across the universe with considerable precision. This technique was central to one of the most startling cosmological discoveries of the 20th century. In the late 1990s, two independent teams of astronomers were using Type 1a supernovae to measure the rate at which the universe was expanding, expecting to find that gravity was gradually slowing it down. Instead, they found that the expansion of the universe is accelerating. Distant galaxies are moving away faster and faster as time goes on. Something is driving space itself to expand at an increasing rate. That something is now called dark energy, and it remains one of the deepest unsolved mysteries in all of physics. The discovery came entirely from measuring exploding white dwarfs. The teams behind that discovery received the Nobel Prize in Physics in 2011 for their work. The prize was awarded for a discovery that grew directly out of understanding what white dwarfs are and what they do when they approach a specific mass threshold. The humble white dwarf, quietly cooling in its binary system, turned out to be one of the universe's most useful measuring instruments. Part 5. Counting the Dead Stars. One of the remarkable things about white dwarfs is how many of them there are. They are by far the most common stellar remnant in the galaxy, and the total population of white dwarfs in the Milky Way tells a story about the entire history of star formation, stretching back billions of years. Current estimates suggest that the Milky Way contains somewhere between 8 and 10 billion white dwarfs. That number is almost certainly a lower bound. Many white dwarfs have been cooling for so long that they have faded below the detection threshold of current instruments. The very oldest and coolest are extraordinarily difficult to find. The challenge of finding cool, old white dwarfs was dramatically eased by the European Space Agency's Gaia mission, a spacecraft launched in 2013 with the primary goal of mapping the positions and motions of over 1 billion stars with extraordinary precision. As a byproduct of its main mission, Gaia identified hundreds of thousands of white dwarf candidates. The distribution of white dwarf temperatures in any survey of the local neighborhood acts like a fossil record of star formation history. Hotter white dwarfs are younger, having had less time to cool. Cooler white dwarfs are older. By counting how many white dwarfs exist at each temperature, astronomers can reconstruct when the stars that produced them were born. This technique, called white dwarf cosmochronology, has been used to estimate the age of various stellar populations in the galaxy. The oldest white dwarfs in the solar neighborhood appear to have been cooling for roughly 11 to 12 billion years, placing the formation of their progenitor stars early in the history of the Milky Way. The nearest known white dwarf to our solar system is a companion to Sirius, the most luminous star visible in the night sky from Earth. The companion, called Sirius B, was predicted to exist based on the wobbling motion of Sirius long before it was directly observed. It was finally detected in 1862. Sirius B was confirmed to be a white dwarf in the early 20th century when its mass and size were measured. It has a mass slightly greater than the Sun, packed into a sphere about the size of Earth. It is the most studied white dwarf in history and has been central to the development of white dwarf theory. One of the intriguing possibilities the white dwarf population raises is the existence of white dwarfs so thoroughly cooled that they are essentially invisible. These would be extremely old white dwarfs, ones that formed early in the history of the galaxy and have been cooling for so long that their surface temperatures have dropped to only a few thousand degrees. Whether these ultra-cool white dwarfs contribute significantly to the amount of matter in the galaxy that we cannot directly see is an open question. The contribution of very cool white dwarfs to the overall mass of the galaxy is something that astronomers continue to refine as detection technology improves and sky surveys grow more sensitive. The sheer number of white dwarfs in the Milky Way means that in a very real sense, the galaxy is a graveyard as much as it is a nursery. For every star currently burning, there are several dead ones cooling quietly in the dark. The night sky, seen in the right wavelengths, would reveal a universe full of dim, fading remnants, drifting silently through the spaces between living stars. Part 6. Strange companions and stolen mass. Many white dwarfs do not drift through space alone. They exist in binary systems with another star whose presence introduces a complicated and sometimes dramatic set of interactions. The relationship between a white dwarf and a companion star is one of the more varied and surprising storylines in stellar astronomy. When a white dwarf and a normal star orbit each other closely enough, the white dwarf's powerful gravity can pull material off the surface of its companion. This process is called accretion, and it happens because the companion star, if it expands enough or the orbit is tight enough, can overflow its own gravitational boundary, at which point the white dwarf's gravity takes over. The material falling onto the white dwarf does not land directly on its surface. It has angular momentum from the orbital motion of the system, which causes it to spiral inward and form a flat, rotating disk called an accretion disk. The material in this disk is heated by friction as it spirals inward, reaching temperatures of tens of thousands of degrees and glowing brilliantly in ultraviolet light and X-rays. As hydrogen accumulates on the white dwarf's surface from the accretion disk, it builds up in a layer that grows progressively hotter and denser due to the weight of newly arriving material pressing down from above. When this accumulated hydrogen layer reaches a critical temperature and pressure, it ignites in a runaway nuclear reaction. This sudden ignition of the hydrogen layer produces a dramatic brightening of the entire system called a nova. A nova is not the destruction of the white dwarf, it is a surface explosion. The hydrogen layer detonates, blasting the accreted material into space at high velocity, producing a bright outburst that can briefly make the system visible to the naked eye. After the explosion, the white dwarf is left behind largely intact, and the accretion process begins again. A system that has undergone one nova outburst is likely to undergo another eventually, once sufficient material has accumulated again. Some systems undergo nova outbursts with remarkable regularity, recurring over decades or centuries. These are called recurrent novae. Astronomers have been able to predict nova outbursts in a small number of well-studied recurrent systems, making them among the very few explosive astronomical events that can be anticipated in advance. The ability to predict a nova and then observe it from the beginning provides valuable data on the physics of the ignition process. Some white dwarf binary systems contain not a normal star, but another white dwarf as a companion. These double white dwarf systems are the result of two stars, both completing their evolution while remaining gravitationally bound to each other. Over time, these pairs lose energy through the emission of gravitational waves and spiral closer together. Eventually, they may merge, producing either a more massive white dwarf, a neutron star, or possibly a Type 1a supernova, depending on the combined mass. The merger of two white dwarfs is one of the more exotic events in stellar astronomy, and the details details of what happens during and after the merger depend sensitively on the masses and compositions of the two objects involved. The variety of white dwarf binary systems, from the classical nova-producing pairs to the double systems spiraling toward merger, reflects the enormous diversity of stellar evolution pathways in the galaxy. Each binary system has its own particular history, its own mass ratio, its own orbital configuration, and its own eventual fate. The white dwarf sits quietly at the center of all of it. Part 7. Cooling through the ages. The defining feature of a white dwarf's existence after its formation is the cooling. Everything else, the spectral changes, the shifts in brightness, the slow transformation of its atmosphere, follows from this single, ongoing process. To understand a white dwarf is largely to understand what it means for something to cool across timescales that have no parallel in human experience. When a white dwarf first forms from the remnant core of a red giant, its interior temperature can be measured in hundreds of millions of degrees. The surface, by the time radiation has carried heat outward to the observable layers, is far cooler than that, but still enormously hot by any ordinary standard. The interior heat drives the entire subsequent history of the object. The rate at which a white dwarf cools depends on several factors. More massive white dwarfs, being denser, have a lower surface area relative to their mass and cool more slowly in certain respects. The composition of the outer layers also matters. A thick hydrogen atmosphere insulates the interior more effectively than a thin one, slowing the rate at which heat escapes to the surface. The interior of a white dwarf is thought to be in a state governed by the behavior of atomic nuclei under conditions of extreme density. As the white dwarf cools, the ions in the interior gradually slow their thermal motion. At a certain temperature, the ions arrange themselves into a crystalline lattice, the way water molecules arrange themselves into ice as temperature drops. This process is called crystallization, and it releases a small amount of energy as it proceeds, a latent heat similar to the heat released when water freezes. This extra energy source causes the white dwarf to cool more slowly at a certain phase of its evolution than it would otherwise. Astronomers, using data from the Gaia mission, found a clustering of white dwarfs at a particular temperature range consistent with this slowing. The idea that the interior of a white dwarf is a crystalline solid made of carbon and oxygen is striking when you dwell on it. The white dwarf, in its final cooled state, would be something like an enormous diamond-like structure at planetary scale, compressed by the weight of a star. The crystalline arrangement of carbon nuclei in a dense lattice makes the comparison reasonable, if not chemically precise. As a white dwarf cools through the range of temperatures where current instruments can detect it, its color changes in ways that can be tracked observationally. The hottest white dwarfs glow brilliantly in ultraviolet light. As they cool over hundreds of millions of years, they shift into the visible range and appear white, then yellow, then orange. Cooler still, they redden further, and their total brightness drops dramatically. White dwarfs, cooler than about 4,000 degrees, present a particular puzzle. At these temperatures, the atmospheres of hydrogen-rich white dwarfs become less transparent than at higher temperatures, a phenomenon where pairs of hydrogen molecules interact in ways that absorb infrared light. This actually causes some very cool white dwarfs to appear bluer than slightly warmer ones, because the infrared light is absorbed and emission shifts toward shorter wavelengths. The very coolest white dwarfs currently known have surface temperatures of around 3,000 to 4,000 degrees, comparable to the coolest red dwarf stars, and they are so faint that finding them requires dedicated, deep surveys. These are white dwarfs that have been cooling for many billions of years, some perhaps for nearly the entire current age of the universe. The cooling of a white dwarf is one of the few processes in astronomy expected to continue essentially forever, or at least for timescales so long that the word forever becomes practically appropriate. The universe is currently about 13.8 billion years old. A white dwarf that formed early in cosmic history has been cooling for perhaps 10 or 11 billion years and has barely begun the journey ahead. Part 8. The Pulsar Cousins. White dwarfs exist in the context of a broader family of stellar remnants, and understanding them is enriched by knowing something about their cousins, the objects that form when stars more massive than white dwarf progenitors reach the end of their lives. These are neutron stars, and the contrast between them illuminates what makes each type of remnant distinctive. When a star more massive than about 8 times the mass of the Sun reaches the end of its life, it does not simply shed its outer layers and leave a white dwarf behind. The core is too massive for electron degeneracy pressure to support it. The electrons and protons in the core are forced together under crushing gravity, combining to form neutrons. The resulting object is held up not by electron degeneracy pressure, but by neutron degeneracy pressure, an analogous quantum mechanical effect involving neutrons rather than electrons. The result is a neutron star, an object typically containing 1 to 2 times the mass of the Sun, compressed into a sphere only about 20 kilometers across, comparable in size to a city. The density of a neutron star is almost incomprehensible. A teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. Gravity at the surface of a neutron star is about 200 billion times stronger than gravity at Earth's surface. It represents matter pushed to the absolute edge of what physics allows before collapse becomes inevitable. Neutron stars are born spinning rapidly, a consequence of the conservation of angular momentum as the collapsing core shrinks dramatically in a fraction of a second. Some neutron stars spin hundreds of times per second. Those that emit beams of radio waves from their magnetic poles clouds and sweep those beams across Earth with each rotation are detected as pulsars, producing rhythmic pulses of extraordinary regularity. The comparison between white dwarfs and neutron stars highlights the role of mass in determining the fate of a stellar remnant. White dwarfs are held up by electron degeneracy. Neutron stars are held up by neutron degeneracy. Both represent quantum mechanical pressure fighting against gravity. But there is a limit to neutron degeneracy pressure as well. Beyond that limit, gravity wins entirely, and the remnant collapses into a black hole. White dwarfs, then, occupy a specific range in this hierarchy of density. They are denser than any ordinary matter, but less dense than neutron stars, which are themselves less dense than black holes, where the concept of density effectively breaks down entirely. One way to appreciate the difference between a white dwarf and a neutron star is to consider the surface gravity of each. On a white dwarf with the mass of the Sun and the radius of Earth, the surface gravity is roughly 300,000 times that of Earth's surface. Extraordinary by any ordinary standard, but modest compared to a neutron star. On a neutron star, the surface gravity is so extreme that falling from a height of 1 meter would result in impact at a significant fraction of the speed of light. The energy released by that impact would be comparable to a nuclear explosion. Nothing about any macroscopic structure could survive such conditions for even a fraction of a second. White dwarfs, extreme as they are, represent the gentler end of this spectrum of stellar remnants. Their surface gravity is enormous, but manageable by comparison. They are the cooling embers of ordinary stars, and while the physics that governs them is exotic, the objects themselves have a kind of quiet stability that neutron stars and black holes entirely lack. Part 9. The Darkness Approaching. To follow the long-term future of white dwarfs is to follow the long-term future of the universe itself, because white dwarfs will outlast nearly everything else. The stars currently burning in the night sky will be gone. The gas clouds that form new stars will be exhausted. The universe will grow quieter and darker, and through all of that, white dwarfs will still be here. The current era of the universe is sometimes called the stelliferous era, meaning the age of stars. It began with the formation of the first stars a few 100 million years after the Big Bang, and will continue for trillions of years into the future, long past the point where our sun will have exhausted its fuel and left behind a white dwarf of its own. But the stelliferous era has a finite duration, and its end is already written into the amount of gas available for star formation. Stars are born from hydrogen in molecular clouds distributed throughout galaxies. As stars form, burn, and die, they process that gas and return some of it to the interstellar medium, but not all of it. A significant fraction is locked permanently into stellar remnants. Over time, the reservoir of star-forming gas decreases. New stars form at a lower rate. The galaxy grows quieter. Eventually, the gas available for new star formation is effectively exhausted. The smallest stars, the red dwarfs, which are far less massive and far more fuel efficient than the Sun, will continue burning long after the Sun has become a white dwarf. Some red dwarfs have lifetimes measured in trillions of years. For perspective, the current age of the universe is about 13.8 billion years. A trillion years is roughly 70 times that. The smallest red dwarfs will burn for far longer still, but eventually they too will exhaust their hydrogen and leave behind white dwarfs of their own. When the last red dwarf star finally fades, the universe will enter a new era, sometimes called the degenerate era. It will be a universe populated almost entirely by white dwarfs, neutron stars, and black holes. There will be no new stars forming. There will be no active stellar fusion anywhere. The only light will come from the slowly cooling white dwarfs, growing dimmer with every passing age. Even in the degenerate era, occasional events will punctuate the long silence. Two white dwarfs in a binary system will sometimes spiral together and merge, producing a brief brightening. A wandering body might occasionally stray close enough to a white dwarf to be consumed, producing a temporary flare. But these events will be rare and growing rarer as available material is slowly exhausted. The timescales of the degenerate era are almost impossible to communicate meaningfully. The current age of the universe would fit inside the first fraction of 1% of this era. It is expected to last for something on the order of 10 to the power of 37 years or longer, depending on whether protons eventually decay, a question that remains unsettled in physics. Through most or all of this time, the white dwarfs will be cooling. The most recently formed ones will still be relatively warm in the early degenerate era. The oldest ones, those that formed early in the history of the universe, will have been cooling for so long that they will have reached temperatures close to the ambient temperature of the universe itself. As the universe expands, the faint background radiation that currently permeates all of space will continue to cool as well. White dwarfs cooling toward this ambient temperature will eventually reach a point where they are no longer warmer than the space around them, where they emit no more radiation than they absorb from the surrounding universe. At that point, they will have become something that may not yet exist anywhere in the cosmos: a black dwarf. Part 10. Black Dwarfs and the Final Dark. A black dwarf is the theoretical endpoint of a white dwarf's cooling. The cold, dark, inert remnant that a white dwarf becomes when it has radiated away essentially all of its heat and reached thermal equilibrium with the surrounding universe. No black dwarfs are thought to exist yet anywhere in the observable cosmos,
the universe is simply not old enough.
The minimum time for a white dwarf to cool to black dwarf temperatures is estimated to be somewhere around a quadrillion years, and that is for the lowest mass white dwarfs. More massive white dwarfs, being hotter and denser, would take longer still. The universe is currently about 13.8 billion years old. A quadrillion years is 100,000 times that.
This means the black dwarf is a purely theoretical object, an extrapolation from well-understood physics into a future so distant that no current astronomical observation can directly inform it. We know white dwarfs cool. We know the cooling slows but never stops. We know electron degeneracy pressure will maintain the white dwarf's structure indefinitely. The conclusion follows from these facts alone.
A black dwarf, once it exists, would be a sphere roughly the size of Earth, containing roughly the mass of the Sun, or less, with a surface temperature indistinguishable from the temperature of the surrounding space. It would emit essentially no radiation. It would be invisible to any detector that depends on electromagnetic emission.
It would be detectable only through its gravitational influence on nearby matter, if any nearby matter existed to be influenced. In the era of black dwarfs, the universe will have grown so sparse and cold that nearby matter may be an increasingly rare concept. The distances between things will have grown to incomprehensible scales as space continues to expand.
The composition of a black dwarf would depend on the mass of the white dwarf it descended from and the elements present in that white dwarf. Carbon and oxygen make up the bulk of most white dwarfs. In the interior, as cooling proceeds over unimaginable timescales, the nuclei would settle into the lowest energy crystalline configuration available to them. Whether this crystalline interior would maintain any particular stability over even longer timescales is uncertain. Some theoretical models suggest that over timescales of 10 to the power of 65 years or longer, quantum mechanical tunneling effects might allow the nuclei in the interior to slowly rearrange themselves into even lower energy states, possibly converting much of the interior toward iron, the most stable nuclear configuration.
If protons are not stable, a possibility that some extensions of standard particle physics allow, but which has not been confirmed experimentally, then even black dwarfs would eventually dissolve. Proton decay would slowly erode the material of the black dwarf, releasing energy in tiny amounts over timescales far longer than the current age of the universe. The black dwarf would quietly evaporate into almost nothing. If protons are stable, as the standard model of particle physics suggests, then black dwarfs might persist for essentially arbitrary lengths of time. The only processes that could eventually affect them would fall outside the reach of any current physical theory. In that scenario, black dwarfs become the final persistent form of ordinary matter in the universe.
There is something deeply quiet
about that image. The universe began in a state of almost unimaginable heat and density, with energy radiating in all directions and matter forming from pure light in the first fractions of a second. It built stars, galaxies, and all the complexity that followed. And it ends, or very nearly ends, with cold, dark spheres drifting through an empty and frigid void, the last embers of all that brilliance, finally and completely dark. And on that note, we come to the end of tonight's journey through the long, slow dark of white dwarfs. From the moment a star like our sun sheds its outer layers and leaves behind that small, dense, impossibly hot remnant, through the billions and trillions of years of patient cooling, through the binary systems and nova explosions, through the crystallizing interiors and the fading light, all the way to the theoretical black dwarf, drifting cold and silent through a universe grown very nearly empty. White dwarfs are not the universe's most dramatic objects. They simply cool, slowly, steadily, across timescales that make the current age of the universe look brief. And in that patience, in that quiet persistence, there is something genuinely worth sitting with for a while. Whether you made it all the way through or drifted off somewhere around the crystallizing interior, I hope the cosmos gave you a little peace tonight. Thank you so much for joining me on the Nocturnal Astronomer. Until next time,